Good morning, Jean-François, Chrysalide Engineering. Happy New Year. This time we are working on a software and a hardware project, which is a overspeed supervision and a speed control system for a real mechanical hardware system, a hydraulic turbine. On this project, using this board and with a custom firmware, we are going to use the analog input and supervise the speed of the machine through pulses. We are counting the pulse through timer and calculating the shaft RPM. According to the speed, we are going to send orders to the machine control, which is speed plus, speed minus, and main valve shut off in case of emergency and overspeed. The peripherals used in this microcontroller include the ADC and the timer 1, which is a 16-bit channel timer. The ADC can work about 200 kHz, and because of the clock and the parameters we are using, we will reduce to about 100 kHz sampling, which is fine for us, and as the pulses are measured to be above 1 millisecond. We also needed to develop the boards that issues the pulses. The speed detection is just a coil and a magnet, and then we have an amplifier and a pulse generation. The signal input is a 100 millivolt sinus pulse, and the output is from 1.5 to 5 volts from 1 millisecond to 10 or 15 millisecond square edge pulse, roughly speaking. We see the design over here. The original design was with 2 operational amplifiers. I then breadboarded a more simple design with 2 inverter amplifier transistors. The first one is also doing impedance adaptation, and the second stage is a 33 times amplifier to make the output edges. And we see the 2 of the boards designed over here, but the second board only should be manufactured, and it is right now in the breadboard setup and proves to be working fine. What we see is the first stage with a coil, a low-pass filter, and a transistor to change the impedance and to amplify the signal from 100 millivolt to 200 millivolts. Right over here we have this stage. There is a potentiometer to set up the transistor polarization on the best optimal value. Then we have a DC filter, this capacitor, and then we have a second stage with a 33 amplifier, inverter amplifier, and our potentiometer to set up the polarization for the transistor and the output stage. We also have a low pass filter again for EMC reasons, because I had issues with the stepper motors we were detecting and shopping on the output just due to the transitions on the motor coils. And this board issues our pulses, and then we are reading analog in the control board, and we make a calculation to have both an hysteresis and an edge detection on the control system board. That is a PIC microcontroller. This is the edge detection code. We see that we read analog. Basically, we send a go command in the register. Then we wait with the while loop for the ADC to complete, and then we read the registers, and we have a shift for the proper conversion to an integer 16-bit from 2 8-bit registers. And then we apply our thresholds. We have 1.2 volt low, 1.5 volt high, and the hysteresis of 300 millivolts. I use the PICSIM from OceanSoft. We see the code running over here and the microcontroller view on the right side. We have analog 0 pin. We set up 200 up to 400 volts, and we see that 300 doesn't change the state, which is inside the hysteresis range. We can see the registers, working registers, program counter, timer, and we can run slow, run fast, see how much time it takes for certain calculations to perform. So it's a nice tool for this kind of project where we have to debug and to check the performance beforehand. Chrysalide Engineering, it's my work to design the boards, the firmware, and I put a store available for You as a customer, if you are interested to get any of these projects, some of them are available, some of them are still under test and will be put on the website when available. And you can get your hands on for projects of your own. So thanks to participate and get the boards if you're interested to get further into this kind of work.